All right, so last time we saw how to add an alcohol through an acid catalyzed hydration. Right, so we have our alkene, and then we add some dilute acid, right? The first step is going to be the formation of this carbocation in the more substituted position. But what we saw is that here we can actually have some carbocation rearrangement, right? So we can have this hydride shift to form this carbocation here, and then this can go on to form this product, whereas if we go from this intermediate, we get this product. And so you can see we have a mixture of products here, as well as some carbocation rearrangement, right? And so remember our saying that if rearrangement can occur, it will. And so we'd like a way to avoid this. To say, for instance, if we only wanted this first product, right? The other issue with this reaction that we learned is that using a strong acid is generally not a good idea, because if you use a strong acid, it can react with other parts of your molecules, right? React with other functional groups. And so at the end of the day, we'd like a better way to have this Markovnikov addition of an alcohol to an alkene. And the way to do this is through oxymercuration, demercuration. And so what we do here is use some mercury acetate. Remember, mercury is Hg, and then OAC is acetate. Right, so all of this is the OAC. And so it kind of depends which source you read, but basically what happens is we have our mercury acetate, our alkene will attack our mercury, kick off an acetate, and then this lone pair can then attack our carbon compound to form this three-membered ring. With a mercury here. So this is called a mercurium ion, right? We have this positive mercury here. And so let's take a look at our carbon mercury bonds for a second here. Right, and then we can imagine breaking either one of these bonds, right? So we can break this bond and go through this pathway, or we can break this bond and go through this pathway. So if we take a look at the green pathway, we have a carbocation right there. And then if we take a look at the blue pathway, we have a carbocation right over here. And right, this would be the formation of a tertiary carbocation, while this is a secondary carbocation. And so this one on the left is better. And so what that results is this carbon right here is more partially positive, right? And so it's more electrophilic. And so in this second step of our mechanism here, we have our nucleophile, usually connected to an H. So usually this is water. And it's going to use its lone pair to attack one of these carbons. And so it's going to attack the more substituted carbon, because this carbon right here is more electrophilic. And then when it attacks this carbon, we'll kick off this bond onto this mercury to form this intermediate. Right, and then so that's our oxymercuration step, right? We've added a mercury to this, and our oxy stands for usually we're adding water across this bond. And so now in the second step, we do the demercuration. To use this, we add some sodium borohydride. Which is NaBH4. And it looks like this, Na plus, BH, H, H, H minus. And even though the boron has the negative charge, hydrogen is actually more electronegative than boron. And so it's actually what bears more of the electron density. So we won't look at the mechanism behind this. This is some kind of radical mechanism and is beyond the scope of this course. But basically what's going to happen is we're going to kick off this hydrogen or kick off this mercury and add a hydrogen in its place. And so our end product here will be our nucleophile with its H on it. And then we just popped off that mercury and left a hydrogen here instead. And so then our last step here, we have a mercury, we have some acetates floating around, we have some sodiums and some BH3s. This acetate will just deprotonate our nucleophile to end up with our final product, where we have our nucleophile still in the Markovnikov position, but now we don't have to worry about any rearrangement, right? So the end result here is that you have your alkene, you add some mercury acetate, maybe some water, and some sodium borohydride, right? So this is our nucleophile H. And that's what's going to be added across our double bond. So if you add water, you're going to add an alcohol. Some other things you could use are like ethanol. Or an amine. And because of the stereochemistry and the radical nature of this mechanism, all of your products, if you do have a stereocenter, they're all going to just be racemic. But the main point of this reaction is that we have a Markovnikov addition. Right, our nucleophile is on the more substituted position. And we have no rearrangement, which is a positive of this reaction.